So in this video, I am going to explain the most important synopsis of hydrogen and its compounds. So this is lesson structure. So first subtopic is position of hydrogen in periodic table. Next about dihydrogen, that means simply H2. Next preparation of dihydrogen, preparation of H2, properties of hydrogen. Next hydrates of hydrogen, this is very important for competitive exams. Next about water, and last hydrogen peroxide preparation and properties. So main preparation important, after that properties, preparation and properties. So first topic, position of hydrogen in periodic table. So hydrogen is first element of periodic table, modern periodic table, and hydrogen has the electronic configuration 1s1. So only one electron in valence shell. Next, dihydrogen is the most abundant element in the universe. Dihydrogen. In some nuclear reactions will be there. In that nuclear fusions, 4 molecules of, that means 4 atoms of hydrogen will be converted to 1 helium. Nuclear fusion reaction. So it is most abundant in the universe. Next, isotopes of hydrogen, protium, deuterium and tritium. I will write here. Protium or simply hydrogen, deuterium, which is also known as heavy hydrogen, and tritium. So symbols are here H11, H12 and H13. Or here we can write D12 also, D12 or T13. So protium, deuterium, tritium are isotopes of hydrogen. Next, this will be also known as ordinary hydrogen. Ordinary hydrogen. So very important. Next, ordinary hydrogen, that means protium has no neutrons. So neutrons can be calculated by using the formula N equal to A minus Z, mass number minus atomic number. Protium has no neutrons. Next, deuterium, which is also known as heavy hydrogen, remember this point, heavy hydrogen, has 1 and tritium has 2 neutrons. So this is about position and isotopes of hydrogen. Next, preparation of dihydrogen. Dihydrogen means simply H2. So in laboratory, it is prepared by reaction of granulated zinc with dilute acids. This is the basic skeleton. So Zn reacts with dilute acids H plus to form H2 gas. So very important. Next, second method, it can be also prepared by action of zinc with alkalis. These two reactions are very important. So based on these two reactions, we can say zinc can react with dilute acids or alkalis. Very important reaction. So zinc reacts with, say, dilute acid gives, so Zn2 plus H2 gas will be released. Reaction with acids. Next, similarly, zinc reacts with alkalis. Alkalis means bases to form Na2ZNO2 plus H2 gas. Remember these two, very, very important. So zinc can react with acids as well as alkalis, that is bases, to release H2 gas. Next, commercial production of dihydrogen. Commercial means manufacture or industrial preparation or large scale preparation. So this can be done by electrolysis of acidified. Acidified means by the addition of H plus or alkaline water containing OH minus ions by using platinum electrodes. That means simply electrolysis of acidified or alkaline water by using platinum electrodes. Platinum electrodes are inert electrodes here. So simple reaction, H2O decomposes to H2 and O2. H2 will be released at cathode, O2 will be released at anode. That is also important. H2 at cathode and O2 at anode. You can collect the hydrogen at cathode, oxygen at anode. Remember that point. Next, very high purity of dihydrogen, that is approximately 100%. It can be obtained by electrolysis of warm aqueous barium hydroxide. That means simply aqueous BaOH twice. Aqueous means that also contains water. Water with BaOH twice. So by using nickel electrodes. Nickel electrodes also inert electrodes. It gives highly purity hydrogen. That means approximately 100%. 99.95 means approximately 100. Next, reaction of steam on hydrocarbons or coke. Coke means form of carbon, electropic form of carbon. At high temperature in the presence of catalyst gives hydrogen. This is the basic skeleton. CnH2n plus 2 hydrocarbon plus H2O. H2O means here steam. At 1270 kelvins in the presence of nickel catalyst can give H2 gas. Next, mixture of CO and H2 is also known as water gas or syngas or synthesis gas. A very, very important topic. CO plus H2 combination, water gas, syngas or synthesis gas. Next. So properties of hydrogen. So first, physical properties. It is colorless, odorless, tasteless and combustible gas that can react with oxygen quickly. Next, it is lighter than air and it is insoluble in water. We know water is polar solvent, H2 is non-polar, therefore insoluble. Next, chemical properties. Reaction with halogens. It reacts with halogens to form corresponding halides, HX. Here X may be F, Cl, Bri halogens. Next. Here reactivity order of halogens. F2 highest, Cl2 and Br2 are moderate and I2 is very slow and reversible. Reactivity order. Reactivity order. Fluorine is most active even in dark. So I2 is very slow and reversible reaction. Next, reaction with dioxygen. That means H2 combines with O2 to form H2O in the presence of catalyst or heating. So delta H is minus 285, exothermic process. So water is exothermic product which is stable. Exothermic product is highly stable. Next, reaction with nitrogen to form ammonia. So which is famous reaction? N2 plus 3H2 reversible with 2NH3, so which is famously known as Haber's process for manufacture of ammonia. Haber's process. Haber's process for the manufacture of ammonia. Reversible. So delta H for this process is minus 92.6 kilojoules. Here not per mole, kilojoules. So in this catalyst will be Haber's process. Catalyst finely divided iron and promoter molybdenum. Remember these points. Promoter means which increases the efficiency of catalyst. Next. So here ammonia also exothermic product. Is also exothermic, right? Exo product, that is also stable. Next one. So reaction with metals. So very highly reactive metals combine at high temperature to form corresponding hydrates. We will discuss this topic separately. Types of hydrates. Next, reaction with metal ions and metal oxides. See here, metal ion, palladium. Palladium 2 plus. H2 reacts with palladium to form Pd and 2H plus. So it reduces. Reduction reactions. These two reactions are reducing properties. So H2 acts as powerful reducing agent. Therefore, it reduces Pd2 plus to Pd and the CuO to Cu. Next, this is very important, reaction with organic compounds. So here, hydrogenation of vegetable oils using nickel catalyst. Nickel as catalyst gives vanaspati or dalda. Vanaspati or dalda, which is saturated fat. So unsaturated oils reacts with hydrogen in the presence of nickel catalyst gives saturated fat, which is dalda. So in hydrogenation of vegetable oils, nickel is catalyst. Remember that point, previous question. Next, hydroformylation of olefins. Hydroformylation. That means addition of H and CHO. Hydroformylation means addition of hydrogen and CHO to alkenes. So very important. Hydroformylation gives corresponding carbonyl compounds which on further reduction will give alcohols. So here H2 and CO. First these two can react to form HCHO, formaldehyde. So after that, addition of H and CHO2 alkenes will result in the formation of carbonyl compounds, that means aldehydes, which on further reduction will give alcohols, corresponding alcohols. Here RCHCH2 alkene, it gives aldehyde, which on reduction gives primary alcohols. Let that reaction also. If aldehyde is present, that on reduction gives RCH2OH. This one aldehyde gives primary alcohol. So we'll discuss this reaction in detail in organic chemistry. Next, uses of hydrogen. It is used in manufacture of methanol ammonia. Methanol means methyl alcohol or wood alcohol. Next, used in manufacture of metal hydrates. Metal hydrates. Metal hydrates. That means hydrogen can react with S block elements, P block elements and D block elements to form corresponding hydrates. Next, hydrates of hydrogen. Hydrates. So what are hydrates? The compounds of the binary compounds of hydrogen with other elements. The binary compounds of hydrogen with other elements are known as hydrates. So here dihydrogen, that means H2 combines with all elements except noble gases. So because noble gases are inert. So from binary compounds. Binary compounds will contain only two elements, hydrogen and other element, called hydrates. Next, E is the symbol of element with hydrate, EHX, general formula. Next, the hydrates are classified into three categories, very important. Ionic, saline or salt-like hydrates, covalent or molecular hydrates, metallic or non-stoichiometric or interstitial hydrates. Metallic or non-stoichiometric or interstitial. Interstitial positions means gaps between metal atoms in metallic lattice. Next, say about ionic saline hydrates. These are the stoichiometric compounds of dihydrogen with S block elements. So we know S block elements are 1A and 2A groups. 1A and 2A groups. Next, ionic hydrates are crystalline, non-volatile and non-conducting in solid state. These are the properties of ionic compounds, you know. So most of the ionic compounds are crystalline, non-volatile. They do not become vapor easily. And non-conducting, bad conductors in solid state. Next, saline hydrates react violently with water producing dihydrogen gas. So saline hydrates means S block elements, we can write like this. Suppose NaH plus H2O gives, so NaH means Na plus H minus. So H2O means H plus and OH minus. So here NaOH will be formed along with hydrogen. Hydrogen gas is liberated. Next. So lithium hydrates are unreactive due to high lattice energy. This is due to high lattice energy. So to dissociate lithium hydrides, more amount of energy is required, therefore unreactive. Next, one more point. NaH on electrolysis will give Na plus and H minus at anode. Anode means positive electrode, So positive electrode can attract negative ions. Therefore, 2H minus will be converted to H2 with release of 2 electrons. Reaction at cathode, which is negative electrode, it can attract positive species. I am taking here 2 Na plus ions. 2 Na plus, by taking these 2 electrons will be converted to 2 moles of sodium metal. So this is electrolysis. Electrolysis of ionic hydrides. Very, very important. So by the electrolysis, H2 will be liberated at anode and metal will be liberated at cathode. Next. Covalent or molecular hydrates. Covalent or molecular hydrates. So dihydrogen forms molecular compounds with p block elements. P block elements. So P block elements means 13 to 18 groups, except 18. 13 to 17 groups can react with hydrogen to form covalent or molecular hydrates. Next. So these are covalent and volatile compounds. These compounds will be converted to vapor easily. So molecular hydrates are further classified into 3 types here. Electron deficient, electron precise, electron rich hydrates. These 3. Covalent or molecular hydrates are divided into 3 types. So electron deficient means less than octet of electrons. Less than octet. Central atom contains less than octet. That means less than 8 electrons around it. So these are formed by group 13. Example, best example, diborane. Next, these compounds can act as Lewis acids due to electron deficient nature. Electron deficient. Next, electron precise. These compounds have octet around the central atom. So these are formed by group 14. Group 14 elements. Electron deficient group 13, electron precise group 14. Next, electron rich compounds will be formed by 15 to 17. So simply electron deficient will be formed by group 13 elements. Next, electron precise hydrates will be formed by group 14. Next, electron rich hydrates will be formed by group 15, group 16 and group 17. So these contain lone pair of electrons. Central atom contains lone pairs around it. Very, very important. Next, these are Lewis bases. Electron deficient compounds are Lewis acids. Electron rich compounds are Lewis bases. Remember these two. So due to the presence of lone pairs, so these compounds can act as electron donors. Therefore Lewis bases. Next, metallic or non-stoichiometric or interstitial hydrates. These are formed by D and F blocks. Interstitial means gaps between metal atoms in metallic crystal. So hydrogen occupies the gaps between metal atoms in metallic crystal. Those compounds are known as interstitial compounds. So example, see here non-stoichiometric. Stoichiometry will not be there here. 2.87 fractions will be there. Easy to remember. See here, in such hydrates, law of constant composition does not hold. So non-stoichiometric compounds means we cannot write exact formula for that hydrate. Fractions will be there. So only D and F block elements can form non-stoichiometric compounds or interstitial compounds. Next. Next, about water properties. It is colorless and tasteless. Next, water has high freezing, high boiling, high heat of vaporization due to hydrogen bonding. So between two water molecules, this is delta minus and it is delta plus. One more water molecule, delta plus and delta minus. Here there will be formation of hydrogen bond. Intermolecular hydrogen bond. So intermolecular hydrogen bonding means hydrogen bonding between two molecules. Next, water has high specific heat, thermal conductivity, surface tension, dipole moment and dielectric constant. Dielectric constant means that can dissolve maximum compounds in it. Dielectric constant means the power of solvent which can weaken the force of attraction between ionic compound. That means two oppositely charged ions. Simply that can dissolve so many compounds. Most of the ionic compounds are soluble in water due to high dielectric constant of water. Next, structure of water. So in gas phase, water is bent molecule with angle. So bent molecule means you can write like this. So your angle is 104.5 degrees. So geometry bent or angular or V shape in gas phase. Very, very important. Remember angle as 104.5 degrees. It is a polar molecule. Polar means charges will be dipole moment. Delta minus, delta plus and delta plus. Polar molecule. Next, in crystalline form of water, that is ice, it has hexagonal form. Hexagonal form, but at very low temperatures, it becomes cubic form. Hexagonal means, benzene like. Cubic form at low temperatures. Next, structure of ice. So it has highly ordered three-dimensional hydrogen bonded structure. Three-dimensional. Next, oxygen atom is surrounded by four other oxygen atoms. Four other oxygen atoms. That is very, very important. That is previous question also. Geometry, shape. Here I will write structure. So each oxygen is surrounded by, I am taking here central oxygen, OHH. Here again OHH and OHH. Here hydrogen bonding, here hydrogen bonding. Next one more OHH and OHH. In this way, so each oxygen atom is surrounded by four oxygen atoms or four water molecules. So 1, 2, 3, and 4. So tetrahedral arrangement. So very important. Next, chemical properties of water. Chemical properties. So amphoteric nature. That means it acts as acid as well as base. That can donate H plus or that can accept H plus. Amphoteric substance. Next, in Bronsted sense, that means according to Bronsted-Lowry theory, it acts as acid with NH3, base with H2S. Amphoteric nature. That can donate or that can accept proton. So this is the equation. H2O reacts with NH3. So here it acts as donor, H plus donor, forms OH minus NH4 plus. Next, H2O plus H2S. It can accept proton. So in first reaction, it acts as acid. Second reaction, it acts as base. Bronsted acid, Bronsted base. Next, hydrolysis reactions. So due to high dielectric constant means the power of solvent to weaken the force of attraction between two oppositely charged ions. It has very strong hydrating tendency. So hydrating tendency means, suppose if you dissolve Na plus in water, Na plus ions will be hydrated. That means interaction of ions with water is hydration. So this is simply hydration of Na plus. Similarly, Cl minus ions will be hydrated like this. Or simply you can say stabilization of ions in water. So first one hydration of cation, second one hydration of anion. So in this process, some amount of energy will be released. That energy will be hydration energy. So this process is hydration. Hydration means interaction of ions with water. The amount of energy released will be hydration energy. So due to hydration, many ionic compounds are soluble in water. So hydration energy always negative, that is exothermic. So during hydration, some amount of energy will be released, therefore exothermic. So water stabilizes ions simply. Next, hydrates formation, hydrates. So here hydrates means crystalline compounds. BaCl2.2H2O, dihydrate. Next, here also same. CuSO4.5H2O, blue vitriol, hydrated salt, copper sulfate, pentahydrate. So it has a tendency to form hydrates with metals. Next, this is very important topic, hard and soft water. Hard water does not give lather readily with soap due to the presence of calcium and magnesium salts. Next, the water free from soluble salts of calcium, magnesium is soft. Soft water gives good lather with soap. So I will add ions. So temporary hardness is due to bicarbonates of calcium and magnesium. This is very important. These compounds are Ca, HCO3 twice and MgHCO3 twice. These are highly soluble in water. So due to the presence of soluble calcium bicarbonate and magnesium bicarbonate, temporary hardness will arise. Next, permanent. Permanent hardness. It is due to chlorides and sulfates of calcium and magnesium. Chlorides and sulfates, that means CaCl2, CaSO4. Next, Ca, MgCl2, MgSO4. These compounds are responsible for permanent hardness. Remember these ions. Next, temporary hardness is due to presence of bicarbonates or hydrogen carbonates of calcium and magnesium. Bicarbonate is also known as hydrogen carbonate. So it can be removed by either boiling or Clark process. Next, permanent hardness. Due to the presence of chlorides and sulfates of calcium and magnesium, it can be removed by Na2CO3. Washing with Na2CO3, sodium carbonate. And Colgan's process. Colgan is sodium hexametaphosphate. Next, ion exchange process on the synthetic resin method. Here the different types of hardness and their removal. Next, hydrogen peroxide preparation. Simple preparation. Barium peroxide reacts with dilute H2SO4. Barium peroxide BaO2 reacts with H2SO4 to form H2O2. Next, from auto oxidation method. Auto oxidation method. So oxidation of 2-alkyl or 2-ethyl anthraquinol in the presence of it to form anthraquinone and H2. So I will write equation for this. So very important process. 2-alkyl means I am writing here 2-ethyl anthraquinol. Anthraquinol. So we'll write here like this. Oxidation, aerial oxidation. It gives 2-ethyl anthraquinone. That means shifting will be like this. Here H2 is removed. That H2 reacts with O2 to form this compound. Very important preparation. Double bond O and double bond. So first one quinolic form. Next one quinone form. Ketone form, quinone. Plus here H2O2. So first process, that means forward reaction, oxidation. Next on reduction, it will give H2PD and quinol. Equilibrium or reversible process. Quinol on oxidation gives quinone. Quinone on reduction gives quinol. It is auto oxidation or aerial oxidation. Here O2 of air. Aerial oxidation. So next, properties of D2O2. Properties and preparation of D2O2. So H2O2 means hydrogen peroxide. D2O2 means deuterated hydrogen peroxide. Next, K2S2O8 reacts with D2O2 to form, that means D2O to form D2O2. K2S2O8 means potassium perdisulfate that reacts with D2O. D2O is heavy water. Remember here H2O water and D2O heavy water because deuterium is heavy hydrogen. molecular weight increases. K2H2O, it is potassium perdisulfate that reacts with D2O, heavy water, to form D2O2. Next, oxidizing properties. So H2O2 oxidizes black lead sulfide to white lead sulfate. Very, very important. So this reaction can be used in whitening of black lead paintings. PBS will be converted to PBSO for white. Black to white conversion. Next, in alkaline medium, H2O2 oxidizes Mn2 plus to Mn4 plus oxidation. 2 plus to 4 plus oxidation. Next, Mn2 plus to Mn4 plus. Next, reducing properties. Hypochlorous acid to Cl minus ion. Hypochlorous acid. Cl will be plus 1 oxidation state. HOCl, Cl oxidation state plus 1. That will be converted to Cl minus. That means minus 1. Reduction. H2O2 reduces hypochlorous acid to chloride. Next, I2 to I minus. I2 iodine, I minus iodide. This is also reduction, decrease in oxidation state. Next, uses of hydrogen as fuel. Hydrogen releases large amount of heat on combustion. So, it will be also known as clean fuel. Hydrogen is known as clean fuel. Clean fuel. Next, this point is very, very important. Atomic hydrogen and oxyhydrogen torches are used for welding and cutting of metals. They can release large amount of heat. Next, hydrogen is used as rocket fuel. Next, it is used in generation of electricity. Next, uses of D2O. It is used in moderator in nuclear reactants. Moderator means slow down the speed of neutrons in nuclear reactors and in exchange reactions to study mechanism. We will discuss this topic in organic chemistry. So uses also very, very important for competitive exams. So they will ask questions like this: which of the following is correct, incorrect, like that. Next. So worksheet questions, we will discuss worksheet questions one by one. Here first question. Deionized water, or it will be also known as demineralized water, is obtained by passing hard water through. Very important process. There are two types of exchangers will be there. Cationic exchanger, anionic exchange. So when hard water is passed through cationic exchanger, so it exchanges Ca2 plus and Mg2 plus to release H plus ions. And after removal of Ca2 plus and Mg2 plus, the rest water is passed through anionic exchanger. It can exchanges Cl minus ions and SO4 2 minus ions to release OH minus ions. So these two will combine to form deionized water or demineralized water. So this is unfit for drinking. See here options: deionized water. deionized or demineralized water. So here no ions will be present. So this water can be obtained by exchanging both cations and anions. Therefore option D. Both cationic and anionic exchanger one after other. So the synthetic resin method. Synthetic resin method or organic resin method. Very, very important. Option D. Next. Second question. The freezing point of heavy water at 1 atmosphere is. Heavy water means, heavy water D2O. So freezing point at 1 atmosphere will be 3.8 degrees centigrade. So for normal water freezing point is 0 degrees centigrade, but for heavy water 3.8 at 1 atmosphere. Therefore option B. Direct property. Next. So on passing electric current over molten ionic hydrates of S block elements, so what will be the reaction? So ionic hydrates means I am taking NaH as an example. Electrolysis. First it gives Na plus and H minus hydride. So reaction at anode. So anode is positive electrode that will attract negative ions. So 2H minus will be converted to H2 gas with release of 2 electrons. Next, reaction at cathode. Cathode is negative electrode that can attract positive ions. So 2Na plus by taking these 2 electrons will be converted to 2 moles of sodium metal. So simply hydrogen is liberated at anode. At anode hydrogen will be liberated. So option A. Next. The compound used as moderator in nuclear reactants. Now only we have discussed D2O. D2O is used as D2O is heavy water. It controls the speed of neutrons in nuclear reactors. Therefore, it can be used as moderator. So therefore, option C, D2O, heavy water. It controls the speed of fast moving neutrons in nuclear reactors. Most important use of heavy water. Next. Hard water contains ions of. So hard water contains ions of calcium and magnesium. So temporary hardness. Temporary hardness and permanent hardness. So temporary hardness is due to magnesium bicarbonates and calcium bicarbonates. Permanent hardness is due to magnesium chloride, magnesium sulfate, calcium chloride and calcium sulfate. So temporary hardness and permanent hardness is due to calcium and magnesium salts. So option B. Cations are calcium, magnesium common in 2 types. Next. The heat of combustion is highest for heat of combustion. So very important. Heat of combustion I will write here. Orders, different orders will be there. First octane, liquid octane, organic compound. Next LPG. Next CH4, methane. Next H2 gas. Next H2 liquid. This is per mole. If you take 1 mole of compound, this will be the order. Next, one more order. H2 gas, H2 liquid, CH4, LPG and octane liquid. This is per gram. Per gram. Next, third one, octane liquid, LPG, H2 liquid, CH4 gas and H2 gas per liter. Remember these orders. So out of H2 gas, H2 liquid, LPG and CH4, LPG will be having heat of combustion. So heat of combustion is always negative. That means amount of energy will be released in this process. Next. Identify the reactions in which H2 is liberated. Preparations. In first equation, we'll get Zn plus 2 moles of NaOH gives Na2ZnO2 plus H2. H2 gas is released. In second reaction, HCOOH with concentrated H2SO4, here CONC, concentrated H2SO4, dehydrating agent, powerful dehydrating agent, it forms CO plus H2O. Hydrogen will not be released. Third reaction, CH4 plus H2O steam at high temperature, 1270 Kelvin should be there here, 1270 Kelvins under catalyst. It gives CH3OH, methyl alcohol plus H2. Fourth reaction, Zn plus 2H plus gives Zn2 plus H2. Fifth reaction, so C plus H2O. So here 1200 kelvins will be there or 1270. 1270 kelvins. So at high temperature it gives CO plus H2. So hydrogen will be released in 4 reactions. So 1, 3, 4, 5. So 1, 3, 4, 5 means option A. Remember all these reactions, very important. So temperature also important. Next. Which of the following is not a method to remove permanent hardness of water? Permanent hardness. See here, Clark process or Clark method. CaOH twice can be used, which is slaked lime. Slaked lime. It is used for temporary hardness. Temporary hardness. Not for permanent hardness. Therefore, option A. Next. Identify correct statement from the following. Correct statements. So, formula of Kalgan. Sodium hexametaphosphate Na6PO3 6 times. That is correct. Next, exhausted permutate is regenerated by using KCl solution is given. This is wrong. So that can be regenerated by using NaCl solution. Exhausted permutate is regenerated by aqueous NaCl solution, which is brine solution, not by KCl. Next, calcium stearate is soluble in water. Calcium stearate is stearic acid derivative. Stearic ion is C17H35 COO twice Ca. This is calcium stearate, that is soluble in water, ionic compound. Next, in ice crystals, each oxygen is surrounded by 4 oxygen atoms. That is also correct. In ice crystals, each oxygen is surrounded by 4 oxygen atoms. Wait 1 minute. Each oxygen is surrounded by, see here, we'll check once. So water molecule structure, you can write like this. Here H2O. So clearly we can observe structure. So here hydrogen bondings will be there. See here, each oxygen is surrounded by 4 hydrogens, not 4 oxygens. Therefore, last statement is also wrong. Therefore, 1 and 3 only. 1 and 3. Option C. Each oxygen is surrounded by 4 water molecules, not 4 oxygens. Each oxygen is surrounded by only 4 hydrogen atoms or H plus ions. Next. Very important. X plus D2O gives C2D2. C2D2 means deuterated acetylene. Deuterated acetylene. That means CaC2 plus D2O gives CaOD twice plus C2D2. Deuterated acetylene. Very important. Next, Al4C3 plus D2O gives AlOD thrice plus CD4. Deuterated methane. So therefore, CaC2, calcium carbide and aluminum carbide. Option D. So with water they can release acetylene and methane. With heavy water they can release deuterated acetylene, deuterated methane. Next. The metal oxide among the following is H2O2 on treatment with dilute acids. Simple. BaO2 plus dilute H2SO4. Ice cold solution of H2SO4 gives BaSO4 plus, you can write like this, BaSO4 and H2O2. Yes, this is preparation of H2O2. Barium peroxide. Barium peroxide. Structure will be like this. Cyclic form. -1, -1 and +2 oxidation states. Remember like this. Option A. Next. So Colgon is sodium hexametaphosphate. Sodium hexametaphosphate. That means NaPO3 6 times, or we can write Na2 Na4 PO3 6 times. This is the actual formula. So therefore, we can write Na6 P6O18, option C. So it can be used to remove permanent hardness of water. Colgan's process. Next. A 30% solution of hydrogen peroxide is. So we know 100 volumes of H2O2 will be equal to 30% weight by volume of H2O2, which is also known as perhydrol, which can be used as antiseptic. So 100 volumes will be equal to 30%. Here 30% solution is given, therefore it is equal to 100 volumes. Remember this. So if it is 10 volumes, 3%, weight by volume percent. Next. Which of the following hydrate is electron deficient? Electron deficient. So electron deficient means B2H6. Electron deficient. Very, very important. So B2H6 structure will be like this. And one hydrogen like this above the plane. And one hydrogen below the plane. So due to banana bonds. So 3-centered 2 electron bonds. So due to 3-centered 2 electron bonds, B2H6 is electron deficient. So these are bridged hydrogens and these are terminal hydrogens. So bridging hydrogens are unstable due to 3-centered 2 electron bond, which is banana bond. So it will be dissociated to 2 moles of BH3, which is borane, and this one is diborane. So therefore option B, remaining are stable. Next. The metal that produces H2 with both HCl and NaOH. So clearly in synopsis we have discussed the Zn plus 2HCl gives ZnCl2 plus H2 gas. Again Z reacts with 2 moles of NaOH gives Na2ZnO2 plus H2, sodium zincate plus H2. So zinc can release H2 with acid as well as base. Next. Which of the following ions will cause hardness in water? Hardness. Hardness is due to calcium ions and magnesium ions. Next. Here I will change option. Here take one more ion. I am taking here Ba2 plus. So calcium and magnesium ions can cause hardness. So here calcium is present, therefore option A. Option A. Highly soluble compounds of calcium and magnesium can cause temporary hardness and permanent hardness. Next. In the manufacture of hydrogen from water gas, which of the following statement is correct? CO is oxidized to CO with steam in the presence of catalyst followed by absorption of CO2 in alkali. So first we'll get CO. That CO will be oxidized. CO will be oxidized with steam. That means CO will be converted to CO2 with release of H2 gas. So this CO2 reacts with alkali. Alkali means you can take KOH or NaOH. So we know KOH or NaOH can absorb CO2 to form K2CO3 or Na2CO3 to get pure H2. So here H2 will be in the form of steam. So CO will be converted to CO2 with steam in the presence of catalyst followed by absorption into CO2. So option A is correct. CO2 will be removed by alkali to get pure H2. Next. Water softening by Clark process uses. So in Clark process, CaOH twice can be used, which is slake lime. Slake lime. So I will add one example. It can be used to remove temporary hardness. Temporary hardness can be removed by Clark process. That means CaOH twice reacts with temporary hardness is due to calcium bicarbonate or magnesium bicarbonate. So it will give 2 moles of CaCO3, so which is insoluble, plus 2 moles of water. This is insoluble and this is highly soluble. So calcium hydroxide or slake lime can convert highly soluble calcium bicarbonate into highly insoluble carbonate, which can be removed easily. So option B, calcium hydroxide. Next. So ionic hydrates react with water to give. Ionic hydrates means I am taking NaH. So Na plus H minus water H2O. In H2O we will be having H plus and OH minus ions. So Na plus reacts with OH, NaOH plus H2. So we know NaOH is basic or alkaline. Therefore, it gives basic solution due to release of hydroxide. Next. Which reaction shows oxidizing nature of H2O2? Oxidizing nature. So take here H2O2 plus. So in first option I am taking I minus gives here I2. So I2 plus H2O. No need to balance, just I am taking H2O. H2. See here, oxidation state -1. -1 changes to -2. So therefore H2O2 is reduced. Therefore, it acts as oxidizing agent. Oxidizing agent. So here I minus 2, I2. I2 means 0. Minus 1 to 0. Oxidized. Therefore, I minus acts as reducing agent. So clearly H2O2, since it is oxidizing agent, that can oxidize iodide to iodine. So clearly option A. In remaining reactions, H2O2 acts as reducing agent. Important reaction. Next. Identify structure of water in gas phase. So in gas phase, we will be having bent geometry, delta minus, delta plus, and delta plus or 2 delta minus also we can write. So bond angle 104.5 degrees, so which is bent or angular or V shape, and oxen has two lone pairs. This is the structure. Option C in gas phase. Next. So decreasing order of hydrogen bonding in the following: liquid water, ice, and impure water. Clearly, first ice, more hydrogen bonding. Next, impure water, least hydrogen bonding. So liquid water, medium. Therefore, we can write first B, ice has extensive hydrogen bonding. After that, liquid water A. After that, impure water C. This is the option. Simply B. In ice, each water molecule is surrounded by 4 more water molecules through hydrogen bonding. Extensive hydrogen bonding. Impure water has least amount of hydrogen bonding due to impurities. So liquid water, medium. Next. 25 volumes of hydrogen peroxide means. So 25 volumes means H2O2 means, or 25 liters. Here I am taking volume. 25 volumes of H2O2 means 1 volume of H2O2 can release 25 liters of O2 at STP. That is the meaning. 25 volumes means 1 volume of H2O2 can produce 25 liters of O2 at STP. So we can write decomposition of H2O2. 2H2O2 decomposes to 2H2O plus O2. So here 2 into 34 grams can release 22.4 liters. But here 25 liters of O2 will be produced by, say, X grams. Therefore, X equal to 25 into 2 into 34 divided by 22.4 STP volume. So we'll get this value as 74.89 grams of H2O2. Now check the options. So 1 liter marked solution contains 75 grams of H2O. B. So here volume means you can take it as liters or ml. 25 volumes means you can take it as 25 liters. So 1 liter of H2O2 can produce 25 liters of O2. Here you can take like this 25 volumes. 25 volumes will give 25 volumes of O2 at STP, or 25 liters can give 25 liters of O2 at STP. Next. Which of the following compounds can enhance the efficiency of hydrogen storage tank? So hydrogen storage tank for storage of hydrogen, the compounds can be used are Na, Ni5, these are alloys. Ti, TiH2, next Mg, MgH2. These alloys can be used. So hydrogen will not react with these alloys. Therefore, these can be used for storage of H2. So in options, Na, Ni5 is there. Alloys. Next. H2O acts as reducing agent in. Reducing agent. Check here. NaOCl plus H2O2 changes to, I am taking here main compounds only. So here Cl state is +1 changes to -1. Therefore, this compound is reduced. Therefore, this acts as oxidizing agent. Next, O state -1 here. Here O state 0. So which is oxidized. H2O2 is oxidized. Therefore, it acts as reducing agent simply. So option D. NaOCl is reduced, therefore oxidizing agent. H2O2 is oxidized, therefore reducing agent. Next. So assertion reason type. Hydrogen is friendly fuel. That means clean fuel. Right here. Clean fuel. So which is correct statement. Next. Atomic number of hydrogen is 1. It is very light element. So this is also correct. But here there is no relation between these two. So therefore A and B are, that means A and R are true. R is not correct explanation. Therefore option D. Simple. Next question. Here also assertion reason type. So loss of electron from hydrogen atom results in the nucleus of these many picometers. That means size of hydrogen nucleus. So 1.5 into 10 power minus 3 into 10 power minus 12 meters, which is 1.5 into 10 power minus 15 meters, which is Fermi unit. So nucleus size will be in the order of Fermi units, we know. That is correct statement. Next, reason. So proton H plus always exists in combined form. So proton has no electrons. Therefore unstable, and it combines with electron rich compounds to form stable. And H plus here is unstable. So therefore 2 are correct, but no relation between these two. So therefore both A and R are correct, but not correct explanation. Clearly option D. Next. So which are the following can reduce decomposition of H2O2? So H2O2 decomposition. H2O2 decomposition can be reduced by urea, phosphoric acid, next glycerol, the acetonylide. So these compounds can retard the decomposition of H2O2. So urea is present, therefore option B. Next, which hydrate among the following is less stable? So BeH2 is least stable. So because it is electron deficient. Therefore option A. Remaining are stable. NH3 due to hydrogen bonding, that is stable. HF hydrogen bonding is there, stable. LiH, so it has high lattice energy. High lattice and therefore it is also stable. BeH2 due to covalent nature, highly unstable. Next. So statement 1, permutate process is more efficient when compared to synthetic resin method. So which is wrong. Synthetic resin method results in the formation of soluble sodium salts. This is also right. So synthetic resin method more efficient than permutate process. So why? Because synthetic resin method exchanges both cations and anions. Both will be exchanged. Here permutate process, it exchanges only cations. Only cations. Therefore, synthetic resin method is more efficient. Next, sodium salts will not be possible in synthetic resin method. So, cationic resins will contain in synthetic method. Cationic exchanger will contain RCOOH or RSO3H, that means carboxylic or sulfonic groups. Anionic exchangers will contain ammonium hydroxides. Here we will not get sodium salts. Therefore, both statements are incorrect. Option D. So this is the end of the chapter. In next video, I will explain one more chapter. All the best and thank you.